Hello student, my name is Vikas Jha and I have completed my M.Tech from NIT Allahabad in manufacturing engineering, and after completing M.Tech I am teaching this manufacturing engineering from 2017, and I have taught around 20 batches in this 8 months, and today we'll discuss the importance of this manufacturing and we'll discuss the different topics that we have in manufacturing engineering. Now, before going into the topic, we'll talk about the manufacturing technology, what actually this subject is and what are the things that we will study in this subject. Before going into that each topics, we'll discuss the importance of this subject in GATE. Now, if you will see, its weightage in GATE, it's around 18 to 22 marks. If you will see this paper of 2018, its weightage was 22 marks in set 2, and in set 1 it was around 17 marks. So if you have a good grip on this manufacturing engineering, if you have a good grip on mathematics and engineering aptitude, you can easily score around 50 marks. So it's basically it is 50% of your total marks, that is 100. So to get the good rank and good marks in GATE, you will have to know the manufacturing engineering. You will have to know. Without manufacturing, you cannot get a good rank. You cannot even get more than 50 marks. I can guarantee that. So this subject is very important, and this subject is very easy. If you will see, easy means if you know the formula, if you know the basic concepts, you will be able to solve each and every questions. Each and every question means if you will see the thermodynamics, if you will see the theory of machine, there you will have to visualize the things. Without visualizing, you will not be able to solve any question. But in manufacturing, it's all about the basic concepts and formula. You will see when I will discuss the different topics in manufacturing engineering, right? So why I'm telling you all this, because it's very easy, because you can easily get that 18 to 20 marks from this manufacturing engineering. So in this manufacturing engineering, we'll discuss the different topics like casting process, we'll discuss the metal forming, we'll discuss the machining process, we'll discuss the welding process, we'll discuss metrology, and then SIM, that is computer integrated manufacturing. That is in that topic we'll discuss about that NC machine and how to do the programmings, right? Now, before going into each and every topics like about the castings, metal forming, then welding, we'll tell you which book you have to refer for this subject, right? So basically you can refer the Manufacturing Science by A.K. Malik and Amitabh Ghosh. Then you can refer Manufacturing Technology Volume 1 and Volume 2 by P.N. Rao. And then we have the Manufacturing Science by Kalpak Jain, and you can also refer the Manufacturing Fundamental of Modern Manufacturing by M.P. Gruber. So these are the different books that we have. So Manufacturing Science by A.K. Malik and Amitabh Ghosh. Then you can refer the Manufacturing Technology by P.N. Rao, that is your Volume 1 and Volume 2. Now, you can also refer the Fundamental of Manufacturing Engineering by M.P. Gruber. And so if you will ask me which one is the best for GATE, I will tell you this: Manufacturing Science by A.K. Malik and Amitabh Ghosh. This one is the best book for GATE. Now, if you are studying this Manufacturing Science by A.K. Malik and Amitabh Ghosh, and if you have some doubt, you can refer Manufacturing Technology by P.N. Rao. This one is also a good book for that manufacturing engineering. Then we have this Fundamental of Manufacturing Engineering by M.P. Gruber. Now you can refer this book for this SIM and that NC and CNC machine. So in Manufacturing Science by A.K. Malik and Amitabh Ghosh and Manufacturing Technology by P.N. Rao, Volume 1 and Volume 2, you will not get this SIM and NC. So for that SIM and NC, you can refer this MP Gruber. So now, what I was talking is like, if you have a good grade in manufacturing engineering, and if you have good grade on mathematics, engineering mathematics, and aptitude, you can easily get 50 marks. Now if you are an engineer, so obviously you will be good at engineering mathematics and aptitude. And if you have the basic concept and if you know the formula, you can easily get that 18 to that 22 marks. So it's easy to get that 50% marks in GATE if you know these three subjects. These three, that is manufacturing engineering, engineering mathematics and aptitude. Now this subject manufacturing, no need to visualize the things. If you know the basic concepts, basic principle of all the manufacturing processes, and if you know how to find out the different forces, how to calculate that allowances and different forces in rolling, extrusion, in different manufacturing process, you will be able to solve the question in GATE. Now in manufacturing engineering, since in your engineering, the basic perception about this subject is a theoretical subject. But I'm telling you, this manufacturing in GATE is completely numerical. All the question means out of that 18 marks, 12 marks question will be numerical, and the remaining 1-2 question will be theoretical. So theoretical means we have number of manufacturing process. In that manufacturing process, we will have some defects, right? In casting, so obviously there are number of defects in casting. In metal forming, again there are number of defects in metal forming process. In machining, we have something. So from there you will get some theoretical question and some basic principle of different manufacturing process. From there you will get some theoretical question, and the remaining that 12 to that 15 marks will be completely numericals. So you will get that numerical question from that. So if you know the formula, you know the basic concept, just take that given data and put into that formula and just calculate the result. That is all about that manufacturing engineering. Now, before starting this subject, we'll write down the different topics that we have in manufacturing and what are the things that we are going to discuss in this subject. So, we'll start our discussion with the casting process. So first we'll discuss the casting process, then we'll discuss the welding. After welding, we'll discuss metal forming process. After metal forming, we'll discuss the machining process that we have, and after machining, we'll discuss the metrology. And then we'll discuss the SIM, or is a computer integrated manufacturing. So these are the different topics that we have in manufacturing, and we'll talk about it. Like in casting process, So it is one of the oldest manufacturing process that we have. So basically what we have to do is, suppose if we have anything like this one. Now to make this one we require some raw materials. Okay, we require raw materials. Now that raw material is of no use. Okay, that raw material is of no use. So what we will do is, we'll convert that raw material which is of no use into some product, into this product. Okay, so basically what we are doing is, we are adding value to the raw materials. Okay, we are adding value to the raw material. By adding value to the raw material, we are converting that raw material into a final product. So the raw material which is of no use because of its irregular shape, indefinite size, because of its poor surface finish. So we are adding value to that raw materials and we are converting it into a final product. Suppose this one. Now this product obviously have the definite shape and definite size. It has the better surface finish and this can be used to fulfill some functional requirement. So this is basically the definition of manufacturing engineering. Okay, manufacturing engineering. So how will we define if we have a raw materials? Okay, it's a process of converting the raw material which is of no use because of its irregular shape, indefinite size, poor surface finish, can be converted into a product by some processes. Okay, into a product which will have the better surface finish and better dimensional accuracy and can be used to fulfill some functional requirement. Okay. So in casting process what we will do is, suppose we have the raw material. Okay, we'll melt that raw material. Once we melt it, we'll pour that molten metal into the mold cavity. So that mold cavity is to be made by using some pattern. We'll discuss about that. So that molten metal is to be poured into that mold cavity and then it is allowed to solidify. Now after solidification what we will do is, we'll take out the product by breaking the or separating the mold. So in this way we can convert our raw material into a final product which will have some functional requirement. Now in welding what basically we do is, we join two components. Okay, so it's a joining process. Okay, so to make a product what we will do is, suppose if we have a product which consists of the number of parts, so we'll weld all the different parts to make that final product. Okay, in order to get some that functional requirement or some properties. In metal forming process what we will do is, suppose we have the raw material. In that raw material what we will do is, we'll apply some force by using some die or by using some roller or by keeping that into a chamber and then we'll apply the force by using some ramp. So basically this metal forming is a plastic deformation process. We are deforming the raw material above the yield point. So then only obviously there will be plastic deformation, so that once you release the load, it will not get or it will not come to that original state, original size. Okay, so metal forming process is a plastic deformation process. We are deforming the raw material plastically in order to get the required shape. Now in machining process, basically this is a finishing process. Okay, basically finishing process means, suppose if you are making the product by using that casting process or by using metal forming process, you will not get that much, the surface finish. Now to get the required, suppose if you have to make a cylinder of say 25 centimeter diameter. Now obviously that cylinder requires very good surface finish, and that we are not getting with that casting process or by using some metal forming process. But for that cylinder we'll have to make the good surface finish. So what we will do is, we will remove that extra layer of material from that cylinder. We'll remove the layer of material from the component in order to get the required surface finish. How will we remove that material from the component? By using some kind of tool. Now obviously that tool and the product that should have the good surface finish, it should have some relative motion, then only we can remove the materials. Obviously to remove the material from the workpiece, your tool material, the hardness of the tool material should be greater than the hardness of your raw material or the component. Then only you will be able to remove that material. So in that machining we'll discuss about the the different forces and the mechanism of that chip formation, mechanism of that material removal from the workpiece. Then metrology is basically that science of measurement. So in this metrology, we'll discuss about, how to give that limits and tolerances to the shaft and the hole. Now, because we know it's very difficult to make the component exact to its dimension. Suppose if we have to make a cylinder of say 24.66 mm diameter. Now it's very difficult to make that cylinder whose diameter should be say 24.66 because of some machine error or because of some human error. So it's very difficult to make that exact dimension. So what we do is we give some that limits. Limits means the maximum and minimum permissible dimension to that cylinder. So that by making the component by using some of the process, if your dimension lies within that limits, then we can say that your component is acceptable. Otherwise, we have to reject that. So in that methodology, we'll discuss about how to give that limits and tolerances, what are the different types of fits that we have, what are the different types of fits like clearance fit, transition fits and interference fit. Okay, how to find out that maximum clearance, minimum clearance. Okay, then we'll talk about how to do the inspection of that shaft and hole by using some different gauges like go and no go gauge. Okay, so we'll discuss about all these things in metrology. Now in SIM or in computer integrated manufacturing, we'll discuss about the NC machine, numerical control machine, and CNC machine, and then how to do that programming, how to write that program, and how to identify. Like we have some codes, right? G code and M code. Now again in that we'll discuss about the BLU, basic length unit. Okay. So these are the different topics that we have manufacturing. We'll discuss. So we'll start our discussion with the casting process. But before that, we have to know what exactly that manufacturing technology is. What exactly that manufacturing technology is. This subject, manufacturing technology. So suppose we have some raw materials, right? We have this raw material, we know raw material. And by using this raw material, suppose we have to make some final product. Suppose it is a bolt. We have to make a bolt by using that. Raw materials. Now this raw material is of no use. Why? Because of its poor surface finish. Because of its poor surface finish, irregular shape, and indefinite size. It's indefinite size. Okay, or because of some inadequate material properties. So this raw material is of no use because of the poor surface finish, irregular shape and indefinite size, inadequate material properties. So we cannot use this raw material except throwing on someone's head, because this is of no use. Now we want to convert this raw material into a final product. In our case, it is bolt. Now to convert that raw material into a final product, say bolt, what we will do is, we will do the value addition. So by using some of the manufacturing process, we will convert this raw material into a bolt. Now once we convert this raw material into a final product, in our case it is bolt, now this final product will have the better surface finish and regular shape and definite size and the adequate that material properties. Now this final product can be used to fulfill, it can be used to fulfill some functional requirement. So basically what we are doing is we are adding value to the raw materials. So manufacturing technology or manufacturing is nothing but a value addition process. It's a value addition process by which we are converting the raw material into a final product. So now you can see in this slide that manufacturing is defined as a value addition process by which the raw material of low utility and value due to inadequate material properties, irregular shape and the size, indefinite size, poor surface finish can be converted into a product of high utility obviously and value with definite dimension, regular shape and good surface finish and can be used to fulfill some of the functional requirement. This is basically what that manufacturing technology is. And I have already discussed what are the different manufacturing processes we have by which we can convert this raw material into a final product like casting, metal forming, welding and then machining. These are the different manufacturing process. Then once we convert that final product, we'll do some measurement, okay, and then finally that CNC and MC. We'll discuss that. So we'll start our discussion with the casting process. We'll see how that casting process can be used to convert the raw material into a final product. We'll see that. So first we'll start our discussion with casting process. Casting process. So you can see how the raw material can be converted into a final product. You can see in this slide. Now suppose if you have to make a gun. So suppose if you have to make a gun, how can we use this casting process to convert that raw material into a gun? Now to convert that raw material into gun, what we will do is we will require the pattern. Now pattern is nothing but is the replica of the shape to be produced, but obviously will have some different, but its dimension may or may not be same as that of your final product. So it's the replica of the shape. So what we will do is we'll use the pattern to make the mold. Mold means that mold will be your sand mold. Okay, so by using that pattern we'll make the cavity into that mold. Now once that cavity is made, what we will do is we'll melt the raw material that we have. Now after melting that raw material, what we will do is we'll pour that raw material into a cavity. Now to pour that molten metal into that cavity, we cannot pour it directly. Why? Once we pour that molten metal into the cavity directly, obviously we'll get the defect in the casting. Why? Because of some oxidation and all that. Okay, so to pour that molten metal, what we will do is we require some gating system. We will require some passage through which we will pour the molten metal into the cavity. Now once we pour the molten metal into the cavity, it is allowed to solidify. So now to make that gun, obviously we require pattern. So that pattern will be, it's a replica of the shape to be produced. So obviously that pattern will be same as that of your product. That is your pattern will be that gun. Okay, but its material will be different. So here in our case we are using the plastic, that is pattern. Now it's a gun. Now by using this pattern we'll make the same cavity into the mold. Now once we make the cavity, after making the cavity, we'll melt that raw materials and we'll pour that into the cavity. Now once you pour that molten metal into the cavity, it is allowed to solidify. It will start solidifying. Now once it starts solidifying, after some time it will solidify, right? So after solidification, what we will do is, we'll break that mold. We'll break that mold. Now in some case, like in sand mold, obviously after breaking the mold, we'll take out the final product. We'll take out the final product. Now that, as I said, like to pour that molten metal, we require some passes. Now obviously the material will be in that passage and it will also be solidified. Okay. So after that solidification, we'll have to trim that the material which has been solidified in the passage. So in the slide you can see that. So we'll have to trim that. Once you trim that solidified metal in the passage, obviously you will get your final product. You will get the final product. That is the gun. So if we have to define the casting process, how will we define that? So casting, you can see in this slide, it is written there. So casting is a manufacturing process in which the liquid molten metal is poured into the mold cavity, whose shape is same as that of the casting to be produced. Whose shape is same as that of the casting to be produced means, obviously its shape will be same, but I am not saying that its dimension will be same as that of the casting to be produced. Its dimension may or may not be the same, because in some case we'll have to make the pattern larger in size. In some case we'll have to make the pattern smaller in size, for the various reasons that we will discuss that. Now after that means whose shape is same as that of the casting to be produced. After that pouring that molten metal into the cavity, it will start solidifying and it will allow it to solidify. Once it is solidified, the casting can be taken out by breaking the mold. So by breaking the mold, you can have the product. That is, so by using the casting process, we have converted this into a final product. So you can see the complete steps in the casting process in the slide given here. So in this, what you can see, this is your mold cavity. So here we have the mold cavity. Now, so obviously its shape should be same as that of the product that we want to make. So by using some of the pattern, we'll make this cavity here in that mold. So in this case, the mold is made of that sand. Okay, molding sand. So once we have this cavity, once we have the liquid molten metal, we'll pour this. But to pour that molten metal, we are using some passage. We are not directly pouring that molten metal into the cavity. Why? The question is why? Why we are not pouring the molten metal into the cavity? Why? To avoid the defect in the casting or casting. That is, defect may be your oxidation, that there will be some formation of the oxide. So to avoid that defect, what we are doing is we are using some passage. And in this process, what we have to do, we will have to design this gating system so that to get the product which will be free from defect. So here we are using the passage, right? Through this passage, so this passage is known as the gating system. So it's a passage through which we are pouring the molten metal into the cavity. Now, it's the property of that molten metal that it shrinks when it is solidified. So when it shrinks when it is solidified, so obviously after solidification, we'll get the product which will be smaller in size. Smaller in size as compared to the required size. So what we will do is, so here you can see we are using the riser. So riser is nothing but it's a reservoir of molten metal. Reservoir of molten metal which is used to avoid or which is used to compensate the shrinkages that is taking place during solidification. Okay, so here we are having the mold cavity into which that molten metal is to be poured. Now to pour that molten metal into the cavity, we are using the gating system or the passage. Obviously we will have to design it. Now it's the property of the material that it shrinks during solidification. So to avoid that shrinkage, we are using some reservoir which will supply the extra molten metal into your cavity. So here it is. This is called the riser. It is open riser because it is open to the atmosphere here. Now you can see here we have this flask. So flask is nothing but it's a frame, okay? It's a wooden or it's a metal frame in which we have to make the mold, okay? So obviously it requires that the molding sand should have the adhesive property so that it will adhere. It will get, you know, stick to that flask. Obviously it has the property. So now we have the two parts, right? The top part is what we call that cope, and the bottom part of that flask is called the drag. Okay, so here you can see the top part of that flask is called the cope and the bottom part is known as the drag. Now here you can see this vent. Suppose if you are making the mold by using some metal. Now in case of the molding sand, it has the property which is known as the porosity. Okay, so porosity is the property of molding sand by which whatever the different airs or the gases that is present in the cavity will escape because of its permeability, because of its porosity properties. Okay, is the ability of that molding sand to escape that air or gases present in your cavity or in the getting system. Now in case of metal, it does not have porosity. So we'll have to give some, you know, we'll have to make some hole into that, so that whatever the air or gases that is present into your molten metal will escape that, will escape through this vent hole. Why? To escape, why it is required to escape all that air or gases present in the molten metal? Because the presence of that air or gases in the molten metal will produce the blowholes. Blowholes is a kind of defect in the casting. Now the line or the plane that separates the cope and drag is known as the parting line. The parting line is the line which separates your cope and the drag. That is your top part of the flask and the bottom part. Now here you can see that runner and gate, all these are the part of your gating system. All these are the element of your gating system, and which is very, very important. We'll discuss about it when we'll discuss the design of the gating system. Now here we can see that core. Now core is nothing but, suppose if you have to make a cavity, if you have to make a hollow projection into your casting. So there we use this core. Now it is made of that sand, that is why it is written the core and sand. Now to make that projection and hollow cavity into your casting, we use core. Now that hollow, that is your core, is to be this core is to be placed into your mold cavity. Now once it is placed into your mold cavity, then we will start pouring the molten metal, so that the molten metal will surround this core. And once it is solidified, we will remove that core from that and we will get the cavity into your casting. So basically that core is used to make the cavity into your casting. So these are the, you know, the different basic terms, okay, that you will have to understand before going into that design of that gating system or design of that core, and the time taken to pour the molten metal into the cavity and the time taken by it to solidify. Okay, so it's very important to know all this basic, you know, terminology in casting. So now you can see in the slide different terms that we have in the casting process. Like I've already told you that we'll discuss this as sprue, runner, as sprue well, as skim bob and ingot while designing the gating system. Then cope, as I said, the top part of the flask is what we know as the cope. Then riser is a reservoir of molten metal which is used to solidify, which is used to compensate the shrinkages, because it is the property of the material that it shrinks during solidification. Then the bottom part is known as the drag, and these are the different terms that we have in the casting process. Now we'll write down the different steps that we have in the casting process. What are the different steps that we have to follow to convert that raw material into a final product? So we'll start with the first thing in casting is to make a pattern. First, what we will do is we'll make the pattern. Now this pattern is the replica of the shape to be produced. Its shape should be same as that of the casting to be produced. Now, but its dimension may be same or it may be different from your final product. Now, once we have this pattern, what we will do is we'll make the mold by using this pattern. So then we have the mold making. Now, once we have the pattern, with that pattern we'll make the mold. Now, after making the mold, what we will do is, after making the mold, we'll melt that raw materials. Okay, so melting. We'll melting and pouring. As I said, that once we have that melted that raw material, we'll start pouring through some passage, and that passage is known as the gating system. Now, once it is poured, it will start solidifying. So, solidification. And then once it is solidified, we will do the trimming or some cleaning, I can say. Trimming and cleaning. Trimming and cleaning means, suppose that whatever the molten metal which remains in that passage will also be solidified. So once it is solidified, or the molten metal present in the riser also, so that will be, that will be integral with that your final product. So we'll have to trim that, we'll have to do some machining on that, and then cleaning to remove that the sand particles onto your final product. So that's why we'll have to do the cleaning. So these are the different steps that we have to follow while converting the raw material into a final product. So we'll start our discussion with the pattern making. How will we make that pattern? What are the different materials that we have? Why means its shape should be same as that of your final product? Why its dimension is different? Okay, so we'll start. What actually this pattern is. So we'll start our discussion with the pattern. So as I said, pattern is nothing but the replica of the shape to be cast. So pattern is the replica of the shape. It is the replica of the shape to be cast. Replica of the shape to be cast. Suppose if we have this mold cavity, okay, so suppose this is your parting line. So we'll start pouring the molten metal to this gating system, and we have this is your mold cavity. Mold cavity. So suppose if you want to make a product which is a cube. So if we have to make a cube, so this is your final product. We want to make a cube. Now to make the cube, we require the first step that we require. We will have to make the pattern. Now as I have written that a pattern is nothing but the replica of the shape to be cast. It means the shape of your pattern should be same as that of your final product. It means we require a cube pattern. To make that cube casting, we require the cube pattern. Means its shape should be same. Now this pattern, you can read the different points that we have in the slide. So it gives us the shape of the mold cavity where the molten metal is to be poured and then it solidifies. Okay, so obviously this pattern gives you the cavity, but because by using this pattern only we are making the cavity into the mold where that molten metal is to be poured. Okay, then its shape will be same as that of the casting, that is the replica of the shape to be cast, but its size may be slightly greater or smaller than the size of the casting. Why its size should be greater or smaller than that of the casting? Because it is the property of the material that it shrinks during solidification. So suppose we have the cavity here. Now in that cavity, if you are pouring the molten metal, suppose if you are pouring the molten metal, suppose here we have to make a cube. Say suppose its material is aluminium. We have to make an aluminium cube. So we are pouring this aluminium molten metal into the cavity. So now once that cavity is filled, it will start solidifying. Now once it starts solidifying, it is the property of this material that there will be some shrinkages during solidification. Okay, it shrinks during solidification. Now once it shrinks, means what will happen? We'll have to make the pattern bigger in this case. Why? Once we make the pattern bigger, so it will make the large cavity. Once it makes the large cavity, so after contraction or after that shrinkage, we will get the required dimension of your product. So that is why that pattern size should be greater than, or in some cases where that material does not shrinks, we are having some exception. So in that case, we do not have to give the allowances or will not have to make the pattern bigger. So that is why this pattern shape should be same as that of your casting, but its dimension may be same or it may be different from your final product. So its dimension may be greater than that of your final product, or it may be less than or smaller than the size of the casting. Now the increase or decrease in size as compared to the size of the casting is called allowances. So whatever the increase in size or decrease in size of your pattern, whatever that increase in the dimension that we are giving on the pattern is called the allowances. Now that allowances is given on the pattern to avoid the shrinkages. Means not avoid, to compensate that shrinkages. We are giving these allowances on the pattern to compensate that shrinkages. So here the aluminium there will be shrinkages in the aluminium molten metal during solidification. So in this case, we will make the pattern bigger so that after solidification, we will get the required size of the casting. So you can read the different points that we have about the pattern. Now next point is getting system and riser may also form the part of the pattern. Getting system and riser. Now what will happen? Now to make the cavity into the mold, this is your mold. Okay, this is your mold. Now what is written here is getting system and rising system may also form the part of the pattern. Now this is your riser. This is your riser. Now it is the property of the material that it shrinks during solidification. So once it shrinks, some of the the shrinkages will be compensated by giving the allowances on the pattern. Allowances means making bigger or a smaller pattern. Now some of the shrinkages will be compensated by using riser. So riser is nothing but it's a reservoir of molten metal. Reservoir of molten metal. So here we have this molten metal. So once it starts solidifying, once there is a shrinkages in that molten metal, now this riser will feed the molten metal into the cavity. It will start feeding that molten metal into the cavity. It will start filling that mold cavity to avoid the shrinkages. So if I have to define riser, riser is a reservoir of molten metal which is used to compensate the shrinkages that is taking place during solidification. And this part is what we call the gating system. This is your gating system. This is your gating system. So this is your gating system. Means through this gating system we are pouring the molten metal into the cavity to avoid the different defects in the casting. Now what is written here is this gating system or the passage and the riser may also form the part of your pattern. Why it is written? Because to make that passage and riser, again we'll have to make the cavity in the mold. So it may also happen that obviously that pattern, suppose here to make this cube we require that cube pattern. So this is your cube, this is your cube. Now that pattern, suppose this is your gating system and this is your say riser. Okay, this is your riser. So this is your final pattern. This is your final pattern. So here your pattern also contain the gating system and riser. So now this pattern with that riser and gating system will keep that into that flask and will fill that flask with the sand. Okay, so after removing that pattern from that mold, we'll have the cavity which is the final product, and also we'll have the cavity which is your riser and the pattern. So through this cavity we'll pour the molten metal and this riser will be used to compensate the shrinkages. So in some cases your riser, that is your riser and gating system, may also form the part of the pattern. Now the pattern may also contain some projection known as the core print to support the core. We'll discuss about what exactly that core print and core is. Basically that core is used to make the project, that is cavity into your casting. Cavity into the casting, suppose if we have, suppose this is core. So here we have to make a cube. So suppose this is your cube. Okay, this is your cube. Now in this cube, if we have to make a cylindrical hole, if we have to make a hole. So if we have to, suppose if you have to make a hole into that cube, how will you make that hole into that cube? We'll use, what we'll do is, we have to make a cylindrical hole. So we'll use that cylindrical pattern or cylindrical core. Now that cylindrical core will place that into the, here, into that your mold cavity. Okay, we'll place that cylindrical core into that cavity. Now once you start pouring, obviously the molten metal will surround that core. So obviously that part of the mold cavity will not get filled because of the presence of the core. So once that molten metal is solidified, we'll remove that core and you will get the cavity into your final product. So basically this core is used to make the cavity into the product, and core print. Core print is used to give the support to that core, because we cannot directly place it into that cavity. Obviously we require some support, right? Support at the end. Then only obviously it will be able to take its position into that mold cavity. So the core print, the extra projection that you are seeing here, so that cavity into your mold is what is known as the core print, to support that core, that extra projection. Okay, and core is used to make the cavity into the mold. Now we'll discuss the pattern allowances. Now, as I said, that once we pour the molten metal into the cavity by making that cavity by using some pattern, it will start solidifying, and obviously during solidification there will be shrinkages, means there will be contraction in the molten metal. There will be contraction in the molten metal. Now that contraction or shrinkages in the molten metal has to be compensated by using, either giving some allowances on the pattern or by using the riser that I said, that is a reservoir of molten metal which is used to compensate the shrinkages. So either it has to be compensated by riser or by using the pattern. We'll see which allowances or which shrinkages is to be compensated by whom, that by riser or by pattern. Now suppose if we have to, so suppose this is your, say this is your cavity that we saw that, okay. So suppose this is a rough, and here we are using the riser. This is your riser, okay. Now molten metal is poured into that cavity and start solidifying. This molten metal starts solidifying into the cavity. So there will be shrinkages. Now suppose here in our case we have to make an aluminium, okay, aluminium cube or anything, either we have to make a cube by using the material steel, okay. So what we will do is, suppose in our case it is aluminium, and is it required to pour that molten metal at its melting point? Because in that cavity we are pouring the molten metal. So obviously if we have a raw material, suppose we have this raw material, say this is aluminium raw material. Now by using this raw material we have to make the final cube. We have to make the final cube. So first what we will have to do is, we will have to melt this raw material. Then only once we melt this raw material, then only we will pour that molten metal into the cavity. Now to melt this raw material, what we will do is, to melt that, so initially say it is at room temperature. So room temperature, say, directly I can write, it is at room temperature. Initially it is at room temperature. So what we will do is, we will apply the sensible heat, okay. We will supply that sensible heat. After supplying the sensible heat, what happens? The temperature of the aluminium will reach to its melting point, okay. So it will reach to its melting point, MP. Now this is the melting point, okay, melting point. Once the temperature of the aluminium reaches to melting point, what we will do is, we will supply the widget. It will be latent heat, okay, latent heat. So once we supply that latent heat, this solid aluminium will get converted into your, here we have the molten metal. So in this case, the temperature will increase. Temperature from the room temperature to the melting point temperature. In case of the latent heat, the temperature will be temperature will remain constant. So at constant temperature we are supplying the heat. Now that solid aluminium will get converted into the liquid molten metal. Now the question is whether we'll have to pour that molten metal at the freezing temperature, or will we have to, we'll have to give some degree of superheat. So suppose its melting point temperature of aluminium is say 560 degrees centigrade. Okay, this is the melting point temperature. Now what will happen if you will pour this molten metal at the melting point temperature, that is at 560 degrees centigrade, using through this passage where we have this gating system. So before filling this cavity, before filling this mold cavity, it will solidify somewhere, right? It will solidify somewhere in the passage. Suppose it will solidify somewhere in the passage. So once it is solidified somewhere in the passage, it will not be able to fill the complete cavity if we pour that molten metal at 560 degrees centigrade. Now to avoid the non-filling of that cavity, or to avoid the solidification in the gating system, what we will do is we'll give some degree of superheat. Means we'll heat the molten metal above this 560. So say we are giving some degree of superheat is say 110 degrees centigrade. Okay. So basically what we will do is this 0 and that 7 and 6. Okay, so 660 degrees centigrade, 670 degree. Okay. So we'll pour that molten metal at 670 degree. So what we are taking is melting point is say 660 degree. Okay, 660. So 660, 0, 7, 7. So 770. 770 is the temperature at which we will pour that molten metal into the cavity to avoid the solidification in the passage. The molten metal should not get solidified in the passage. Otherwise what will happen? We'll get the defect because the cavity is not completely filled. So you will not get your required casting. So to avoid that solidification in the passage, what we are doing is we are giving some degree of superheat. We are heating that molten metal above its melting point. We are not pouring that molten metal at melting point temperature into that cavity. We are giving some degree of superheat. So in our case, we have taken 110 degrees centigrade. So we are pouring that molten metal at 770 degree centigrade into that mold cavity. So now once we have poured that molten metal, okay, once we have poured that molten metal, now this molten metal will start solidifying. So once it starts, means we have poured. So this 770 degree centigrade, this 770 degree centigrade is the temperature at which we pour the molten metal. It is the temperature at which we are pouring it into the cavity. So this temperature is known as pouring temperature. Pouring temperature. This is your pouring temperature. The temperature at which we are pouring into the mold cavity. Now we have poured, it starts solidifying. So during solidification, what will happen? During solidification, its temperature will decrease from that pouring temperature to freezing temperature. So pouring temperature, the state of that aluminium is liquid. Again its freezing temperature, it will be liquid. Okay. Now, so during that obviously it will be sensible cooling. So pouring temperature to freezing temperature, it will be sensible cooling. Now at freezing temperature, this is the freezing temperature, here it is liquid. Now will be rejection of heat. So freezing temperature to freezing temperature, here the state will be solid. So at constant temperature, obviously that molten metal will solidify. Now again there will be further cooling of that solid aluminium. So from freezing temperature solid to room temperature solid. So if you will see, there are 3 stages of that cooling. So this is your first stage, this is your second, and this is your third stage. Third stage of cooling of your molten metal into the mold cavity. Now once we are pouring, it will start solidifying, so its temperature will decrease from pouring temperature to freezing temperature. In that case there will be a rejection of the heat. So it's known as sensible cooling. Okay, sensible cooling, because there will be the decrease in temperature. Now during this first stage, what will happen? There will be contraction in the liquid during solidification, during this first stage. Okay. So there will be the contraction in the liquid, and the contraction in the liquid during this first stage is known as liquid shrinkage, or the shrinkages which is taking place during the first stage, or the contraction in that molten metal is known as the liquid shrinkages. Now the second stage is your molten metal at freezing temperature will get converted into the solid at constant temperature. Here the temperature is constant. Okay. So again there will be contraction during that second stage, and this is known as solidification shrinkage. This is known as solidification shrinkage. That is, the shrinkage is taking place during the second stage. Now third one is the last, that is the last stage of that contraction. Again, once this molten metal gets solidified at that constant temperature, there will be further cooling of that solid aluminium from that freezing temperature to the room temperature. And the contraction or the shrinkages taking place during this third stage is what we know as solid contraction. So this is solid contraction. So basically we are having the 3 shrinkages or 3 contraction during this solidification, once that molten metal into your mold cavity gets solidified. Liquid shrinkage, solidification, and solid contraction. Now the question is, we are talking about the allowances on the pattern. Okay. Now, so which of these shrinkages or contraction in this molten metal is to be compensated by giving the allowances on the pattern? The question. Giving the allowances means by making the pattern bigger or smaller. So can I say this liquid shrinkage and solidification shrinkage is to be compensated by making the pattern smaller or bigger? No. These two, liquid and solidification shrinkages, is compensated by using the riser. So that is the function of the riser here. You can see this riser. This is the riser. As I said, this riser is used to compensate. It's a reservoir of molten metal which is used to compensate the shrinkages taking place during solidification. So the shrinkage what I was talking about is liquid shrinkages and solidification shrinkage. So this liquid shrinkage and solidification shrinkage is to be compensated by using the riser. Okay. And the solid contraction, that is the shrinkages that is taking place during this solidification from that freezing temperature to the room temperature, is compensated by making the pattern smaller or bigger. So this is the last stage of contraction which is to be compensated by the pattern, not this liquid and solidification. This liquid and solidification is to be compensated by using the riser, which is a reservoir of molten matter. So once it contracts, this riser will supply the extra molten matter into the cavity, so that that cavity will again completely get filled and you will get the required product. So the last stage here we are seeing solid contraction is to be compensated by using pattern, by giving the allowances of the pattern, or by making it bigger or smaller. Okay. So these are the three stages of contraction that we have in during that solidification. Now the question is how that liquid shrinkages, solidification and that solid contraction is to be specified. How will you specify that all these shrinkages? When we talk about the liquid shrinkages, we specify it by the percentage volume. Percentage volume. Say 2%, 3%, 4%. Okay. Solidification again, it is specified by the percentage volume. Percentage volume. Percentage volume means, suppose we have to make a cube. Suppose its side is, we have to make a cube whose dimensions would be, whose side is 20 mm. So its volume will be 20 cube. 20, side is 20 mm. So its volume will be 20 cube. Now say during solidification there is a contraction, and say there is a liquid contraction and solidification contraction, and it is given that it is 2%. It is 2%. Now they are telling you to find out the size of your product after contraction. So this is the side of your cube. Okay, size of the cube, that is your pattern. Now there is a contraction of that 2%, so we'll find out the volume. Now we'll find out the final, we have to find out the final size of your product after that contraction. So the contraction, that is shrinkages, is 2%. It means we are having the 98% of the volume. So this will be your final volume. This is your final volume after that 2% contraction. Okay, so 0.98 into 220 cube will be equal to your final volume. Now if you will divide it by 1/3, you will get the final side. Means after contraction, whatever the cube that you are getting, you will get its dimension of the cube after the contraction. Okay. Now, how will you specify the solid contraction? This liquid shrinkage is to be specified by the percentage volume and solid contraction. So this solid contraction is to be specified by giving that percentage on the dimensions. Percentage, this is the percentage on that linear dimension. It is to be specified by the percentage on the linear dimension. So linear dimension means, say 20, say solid contraction is 2%. So 2% of that 20 is a cube, so again it will be 20. This is again 20. So we'll have to give their 2% contraction on each dimension. 20, width 20, height 20. So liquid and that solidification shrinkage is to be compensated, is to be specified by the percentage by volume, and the solid contraction is to be specified by the percentage on that linear dimensions. So this is very very important. Okay, liquid shrinkage, solidification, shrinkage, and solid contraction. Because from these three concepts you will get some question in GATE. Okay, they will give you that as I said, the pattern size, and they will ask you to find out the after contraction what will be the side of your final product, or they will ask you the ratio of the pattern and your casting. If there is a say 2% of liquid shrinkage, 3% solidification, and say 1% your solid contraction. So they will give you that contraction. So the first two stages, that is liquid shrinkage and solidification shrinkage, is to be compensated by using the riser, as I said. And the last stage, solid contraction, is to be compensated by giving some allowances on the pattern, by making the pattern bigger or smaller. So it is a property, for some material it expands during solidification. Okay. For example, in cast iron. In cast iron what happens is, there is an expansion during solidification. Why? Because of the formation of the graphite, because of that graphite flux. Okay. So basically 2.5%, there is expansion of 2.5% if we have the 4.3% of carbon in that. Okay. In case of that grey cast iron. So there is a expansion of 2.5%. So in that case, we do not have to give the allowances on the, or we do not have to use riser, because since there is a 2.5% of expansion of that grey cast iron, so whatever the shrinkage that is taking place during liquid shrinkage and solidification shrinkage is to be compensated by that 2.5% expansion. Now the remaining contraction will be compensated by giving some allowances on the pattern. So in case of grey cast iron, we do not need to give the allowances for that liquid and solidification, because that is to be compensated by the expansion. Because of the graphite, there is expansion. So we do not need to give that, okay, allowances. So we do not have to use this riser in case of grey cast iron. Just we have to give the allowances on the pattern, so that it will compensate that. So there are some materials, in that case we do not need to give that allowances. Now if you will ask me, now which of the material which have the largest that liquid shrinkages, I would tell aluminium. Aluminium have the highest that liquid shrinkages. Okay, liquid shrinkage means solidification shrinkages we have. Okay. So you can refer the some of the books where you will find out the shrinkages that is given on the pattern for different materials like steel, copper, aluminium, okay, brass. You will get that table from where you can remember that different the value of that allowances that is to be given for per that some mm per meter. So for 1 meter, how much mm we have to give the allowances on the pattern. You will get in any book, either in P.N. Rao or in Amitabh Ghosh or in Kalpakyan, you will get that. So in the slide you can see what are the different pattern allowances we have. Shrinkage allowances that I discussed here. Shrinkage allowances. So this solid contraction, to avoid this solid contraction we'll have to give the allowances on the pattern. Then we have the draft allowances. Now, why it is necessary to give that draft allowances? Why it is necessary? Now, we'll talk about it. Why it is necessary to give that draft allowances. Now, we have the mold, we have the sand mold, right? Now, in that sand mold, if we have to make the cavity, we'll use pattern. Now you can see in this slide here, if we have to make the cavity, we'll use that pattern. Now suppose we have to make an aluminium cube. Now to make that aluminium cube, we'll use that cube pattern to make the cavity in the mold. Okay. Now this cube has a vertical surface. So once we filled that flask with that sand, and once we have the mold, we'll have to remove that pattern to get that cavity from that mold. And in our case, we are using the sand mold. So since this cube has a vertical surface, and once you start lifting that pattern from that mold, so what will happen is it will remains in contact with the mold till it comes out of the mold or mold cavity. Okay, so at the last means till the last point it will remains in contact. So because of some machine error or because of some human error, okay, if there is a vibration, so what will happen? It will damage your mold cavity. So once due to that vibration or some error, it is damaging your mold cavity, so obviously we will get the defective product. We will have some defect in the product. So to avoid that damage in your mold cavity, basically what we do is we give some inclination to the vertical surface. We give some inclination in the vertical surface. So you can see here in the slide. So in the first case here we are having the vertical surface of the pattern. So this will cause the damage. Okay, damage to your mold. Okay, so once it is causing the damage to the mold. So what we will do is we'll give some inclination to the vertical surface. What I mean is, suppose we have this pattern initially. So this will cause the damage. Okay, damage. Now what we will do? We'll give some inclination. We'll give some inclination. So this is your inclination. Okay, some degree. 1 to 3 or something. 2 to 3. 1 to 3 degree for that external surfaces. So we are giving some inclination. So what will happen? Once you start lifting, there will be formation of some gap between your pattern and the mold. So even there is a vibration or some error, obviously your cavity will not get damaged. So once it is not get damaged, obviously you will get the cavity or you will get the product free from defect. So that is why it is required to give some inclination in case of the vertical surface. Now the question is, means if you are giving some inclination, so obviously we will have some extra metal in the final product. So this is nothing but the extra layer. This is nothing but the extra layer of material into your final product. Suppose in this case. So this is the extra layer of material that you are having in your product. So is it required? No. So what we will have to do is, this is your required part. This is your required part and this is the extra layer of material. This is the extra layer of material. And this is nothing but the scrap. So what we have to do is, we'll have to remove by using some machining process. Okay. But we have to avoid the damage to the mold. So basically for external surface, this is 7 to 3 degree. You can find out the value of the draft allowances. Okay. For the external surfaces. So for this purpose, we use the draft allowances. Now after the draft allowances, here we have the sake allowances. Now sake allowances means it is the property of the moldings that sand. So basically what we do is we use the wood pattern because it is easily available and it is very easy to give the required shape. But the problem with the wood pattern material is that moisture absorption. So there will be that swelling in that. So it is one of the problem of that. But since it is easily available, it is easy to give shape to that wood pattern. We use that wood pattern. Now, once we are using this wood pattern into that to make the cavity into the mold, so it is the property of the sand that some sand particles will get adhere to that pattern. Now, once it get adhere means again what we do is we shake that pattern. Okay, we shake that pattern little bit. We shake that pattern so that what will happen again due to that shaking, the sand particle will get separated from that pattern. So once it gets separated, now you can easily remove that pattern. Okay. So during that shaking, what will happen? The size of the cavity will increase. During that shaking, size of the cavity will get increased. Now again, this is the problem. So what we will do is, in that case, we'll make the pattern smaller. Okay. Because due to this shaking, the size of the cavity get increased. So you will get the final product obviously greater than the size. So due to the shaking, your size of the cavity will get increased. So what will happen is, obviously the product that you will get after that solidification obviously will be bigger in size as compared to your required size. So in this case, what we will do is, we'll make the pattern smaller. We'll make the pattern smaller so that after shaking you will get the required size of your cavity in which that molten metal is to be poured. So basically this shake alloyance is a negative alloyances. Negative alloyances means pattern is to be made smaller in size as compared to your final product. But because in other cases what we are doing is, we are making the pattern bigger so that after contraction we are getting the required product. But in this case, in case of that shake alloyances, we will have to make the pattern smaller so that after shaking you will get the required size of the casting. But what we will have to do is, in shake alloyances, the shake alloyances is given on the dimension which are perpendicular to that, which is parallel to that parting line. Okay. And in case of draft alloyances, we will have to give the draft alloyances on the dimension perpendicular to that parting plane, on that this vertical surface which is perpendicular to this parting plane. Okay, perpendicular to this vertical surface. Now then we have the machining alloyances. So machining alloyances you can see here. So why it is necessary to give the machining alloyances? Because as I said, means the problem with this casting or the limitation of the casting process is we do not get the required surface finish. We do not get the required surface finish by using that casting or by using some metal forming. And suppose if we have to make a component, we should have a very good surface finish. So what we will do is, we will supply the extra layer of material on the surface, on the different surfaces that we have. So by giving that, by supplying that or by giving some extra layer of material, we will remove that extra layer by using some of the machining process. So by using some of the machining process, we can remove that extra layer so that after removing that extra layer, you will get the required surface finish that is required in your component. For example, in cylinder. So in cylinder, if you will make that cylinder by using casting, you will not get that required surface finish, because this is the limitation of the casting process. So we are giving that, means we are giving the extra layer of material. So for that, we will have to give the machining alloyances. So you can see in this slide, it is given on the side. So side means, suppose if you have to make a solid cylinder, so if you have to make a solid cylinder, if you have to make a solid cylinder, so this is the center, this is the center. So what we will do is, we will give the machining alloyances. So 2 mm, say suppose machining alloyances is 2 mm, so 2 mm on this side and 2 mm on this side. Okay, so this is given, machining alloyances is given on x mm per side. So this x mm has to be removed by using some of the machining process.